Hello, and welcome to the next installment of PLC Fundamentals Analog Calculations Part 2. In this particular presentation, what we'll look at is a pneumatic globe valve that uses a 4 to 20 milliamp signal to control the air pressure, and then the air pressure pneumatically opens and closes the globe valve. We will be looking at calculating the set points. So, given a percentage of open or closed of the valve, we will then calculate the necessary signal from the PLC and then the necessary required PSI air pressure to control the valve. So let's get on with it, shall we? So today we'll be looking at a pneumatic globe valve. A globe valve falls into the control valve family. So basically it's open or closed. In our particular example, we can vary how much the globe valve is open or closed. This positioning of the valve is what we call throttling. So it's not just fully open or fully closed, it is a variable set of positions that it can be in. So how do we adjust how much we throttle this particular valve? Well, it's pneumatic. And so we give it an air supply. This particular example is what we would refer to as a spring closed air open. If you want to consider it as a normally closed valve, then you could do so. But the idea is that when there's no air pressure, then the springs will keep the valve closed. And as you add air pressure, then you'll throttle the valve open, where more air pressure opens a valve more until it's fully open. So how do we control the air pressure? Well, we do that through an electrical signal from a PLC. So we're going to send a 4 to 20 milliamp analog signal into a converter, and that converter will then convert the 4 to 20 milliamp signal into a 3 to 15 psi pressure. Those 3 to 15 psi will then go through an amplifier that's built into the converter and give it enough air pressure to open and close the valve to its required amount. The valve also has a positioning sensor on it. And the positioning sensor sends a signal back to the PLC to let it know exactly where the valve is at any given time. So we send a signal out, and then we receive a feedback loop signal so that we know exactly where the valve is. So a lot of these valves use a current to pressure module. And then that pressure module uses a pressure amplifier. And again, larger valves require much more air pressure. So there's a set of standards, and then there's some independent ones based on the actual application. When it comes to current, our standard electrical requirements would be a 4 to 20 milliamp circuit. So our lower range limit, or 0% or nothing applied, would be anything less than 4 milliamps. Our upper range limit would be 20 milliamps. So that when I apply 20 milliamps, I'm at 100%, in this case, throttled open. So this gives us a span of 16 milliamps, because the range is between 4 and 20 milliamps. A standard set of pressure parameters is 3 to 15 psi. So that gives us a lower range limit of 3 psi, where anything that is 3 psi or less is considered off, or 0%. And anything at 15 psi or greater is our upper range limit, which means we're at 100%. So that gives us a span of 12 psi falling in a range between 3 and 15. We need to remember these numbers as we move forward to calculate our outputs or our output signals for however much we want to throttle our valve open in this particular example. So, our current input to the valve is going to be between 4 and 20 milliamps and have a span of 16. Before the pressure amplifier, the pressure is going to fall between 3 and 15 psi for a span of 12. So these are the numbers we will use to calculate our values. From our previous presentation, we are calculating given the signal or our set point and then calculating our output. For this set of examples or demonstration, we want to find what is our current or pressure set point based on the percent that we want to open this valve. So at 0% open, we are at our lower range limits, which 4 milliamps or less means that the valve is closed or off, or 0%. And that correlates to 3 psi. On the opposite end of the spectrum at 100%, well, our current, our upper range limit, is 20 milliamps. And for our pressure, it's 15 psi. So all of our values have to fall between our upper and lower range limits. So let's do an example. When we rearrange our output formula for our set point, our set point is equal to our span multiplied by our percentage, and then we're going to add our lower range limit. If you recall, our lower range limit is kind of like our offset. It would be 4 milliamps for current and 3 pounds for our PSI. So when we take our set point in this, let's take a look at 15% for our first one. So our percent out is 15%. We're going to multiply that by our span of 16 milliamps, which gives us a value of 2.4 milliamps. Then we got to add our lower range limit back into that of 4 milliamps, which means our set point for 15% has to be 6.4 milliamps for our analog current input to the globe valve from our PLC. So if we were to look at the 15% for our pressure setting, it's the same calculation. Your set point is equal to your span times your percent, and then add your lower range limit, which is 12 psi multiplied by 15%, which gives us about 1.8 psi. Add your 3 back into it, and that gets us to 4.8 pounds per square inch. So let's do one more example together. Let's take a look at 48%, which is almost half. Not quite half, but almost half. So if we were to guess where it would be, we have a 16 milliamp span, half of that is 8, add 4 in. So if we were exactly at 50%, would be somewhere around 12 milliamps, but we're slightly less than 50%. So we should be slightly less than our 12 milliamps. So when we take our 16 milliamps, multiply by our 48% and add 4 back in, sure enough, we're slightly less than 12. That gives us 11.68 milliamps. Let's do the same thing with the pressure. For our pressure, we have a span of 12. half of 12 if we were at 50%. So we're sort of guesstimating our answer. Half of 12 is 6. Add your 3 psi offset into 6, and that gives us 9. So if we were at 50%, we'd be at 9 psi. We're slightly short of that. We're at 48. So when we do our pressure calculation, it works out to be 8.76 psi. Sure enough, close to 9, because it's slightly less than 50%. So I hope that sort of helps you sort out and figure out how to calculate these out. Why don't you go ahead and calculate out the 33%, 66%, 85% on your own. Feel free to pause the video here, calculate them out, and then compare your answers to the ones I'm about to provide. I'll give you a minute now to pause and then sort that out. So how did you get along? Here's the currents, and there's your pressures. If they didn't work out, go back and check how you put those into your calculator, or double check the formula to make sure you wrote it down correctly. These are important calculations to make so that you know how much to blend something in or how much to throttle a valve open or closed, and so that you can make those adjustments. You can put that into an algorithm into your PLC, so as your feedback loop comes back, you know if you need to adjust a temperature by blending liquids in. You can say, I'm at this percent open, I need a bit more, so you can throttle the valve open more. Or I'm at this percent open, I need less, and so you can throttle it back. So that concludes this presentation. I hope that helps you with your calculations, and I'll see you next time. Thanks for watching.